Long before humans walked the earth, North America was a land teeming with colossal creatures and fearsome predators. Vast plains, dense forests, and ancient swamps were home to titans that ruled the prehistoric world. From razor-toothed hunters who stalked their prey with cunning precision to gentle giants whose footsteps shook the ground. This continent held an extraordinary array of life. Each fossil unearthed tells a story of survival, adaptation, and an untamed wilderness where the struggle for dominance shaped entire ecosystems. Join us as we journey through the natural history of the ancient land of America, from the shallow seas of the Cambrian period to the frozen forests of the Pliocene era. The first possible sign of dinosaurs in North America comes from rare and unconfirmed footprints, possibly made by theropod dinosaurs found in the Middle-Late Triassic Peking Formation of North Carolina. However, the most reliable early dinosaur evidence comes from broken pieces of Sishan fossils discovered in the Upper Triassic Dome group of Texas. As time went on during the Triassic period dinosaurs left behind more recognizable remains, allowing scientists to identify them as specific species. Some of the well-known dinosaurs from the later part of the Triassic in North America include Coopis, Chindosaurus, Gojirasaurus, and Tawa. Interestingly, fossils of dinosaurs similar to Tawa have also been found in South America, which tells us important things about how the continents were arranged long ago. During the early Jurassic period, North America was home to dinosaurs like Dilophosaurus, Ankylosaurus coelophysis, which was once called Megapnosaurus, and the early armored dinosaur Scutellosaurus. Scutellosaurus is thought to be the ancestor of all later armored dinosaurs, including stegosaurs and ankylosaurs. The Middle Jurassic period in North America, however, is not as well understood, though we do know that several fossil sites from this time have been found in Mexico. Full of footprints, eggshells, teeth, and bone fragments from theropods, sauropods, and ornithopods have been discovered, but these remains are not specific enough to identify the exact species. In sharp contrast, the late Jurassic period in North America is much better represented. The late Jurassic Morrison Formation, found across several U.S. states such as Colorado, Utah, Wyoming, Montana, New Mexico, Oklahoma, South Dakota, and Texas, is one of the richest sources of dinosaur fossils in the world. The variety of dinosaurs found there is truly amazing. Among the theropods, fossils of Allosaurus, Sauroga, Torvosaurus, Catosaurus, Coelurus, Orthices, Tannel grouse, Stoxosaurus, and Marchosaurus have been discovered. The Morrison Formation is also famous for its many sauropod fossils, including those of Apatosaurus, Diplodocus, Barosaurus, Brachiosaurus, Camarasaurus, Brontosaurus, and Ampicoelius. 3 types of Stegosaurus, Alovaorus, Stegosaurus, and Hesperosaurus, have been found there too. Additionally, the site has yielded fossils of ornithopods like Camptosaurus, Dryosaurus, and Nanosaurus. The Morrison Formation remains one of the most important paleontological sites in the world due to the incredible variety of dinosaurs it has preserved. During the early Cretaceous, many new dinosaurs emerged to take the place of the older ones. While some of the giant plant-eating sauropods were still around, they were no longer as varied or numerous as they had been during the Jurassic. In North America, the early Cretaceous was home to a variety of theropods like the fierce raptors Deinonychus and Utahraptor, the large carnivorous Acrocanthosaurus, and the smaller, more nimble Microvenator. Some of the sauropods that roamed during this time included Astrodon, Brontomerus, and Sauroposeidon. The herbivores of this period were also more diverse than they had been in the Jurassic. Among the many ornithischians, plant-eating dinosaurs, some of the notable ornithopods included Tenontosaurus, Daedon, and Hoplosaurus. The ankylosaur, armored herbivores, began to rise to prominence during this time, gradually replacing the stegosaur species that had been dominant in the Jurassic. Early Cretaceous ankylosaurs from North America, such as Sella and Gastonia, were some of the most well-known. Meanwhile, therizinosaurs like Falcarius, with their long claws and herbivorous diets, were also a part of the early Cretaceous fauna. As the late Cretaceous period began, dinosaurs continued to evolve and diversify. The Sirmian stage saw the appearance of new herbivores like the hadrosaurs, Eolambia, and Protohadros, and small carnivores like the early Tyrannosaur Moros intrepidus, which would eventually replace larger, older predators like cests. These groups continued to thrive as time passed into the Turonian stage, where therizinosaurs such as Nothronicus and larger ceratopsians like Zuniceratops lived. The Campanian stage, which followed, was a time of extraordinary dinosaur diversity. Theropods of all sizes and shapes roamed the land, including the famous tyrannosaurs Albertosaurus, Gorgosaurus, and Daspletosaurus, as well as smaller but deadly raptors like Dromaeosaurus, Saurornitholestes, and Bambiraptor. Among the plant-eaters, ceratopsians such as Penosaurus, all of which were known for their distinctive crests and horns. As the Cretaceous period drew to a close in the Maastrichtian stage, the diversity of dinosaurs began to decrease compared to the Campanian. Herbivorous dinosaurs, such as the giant sauropod Alamosaurus, the ceratopsians Triceratops and Torosaurus, and the unique Pilosaurus and Stygimoloch, known for their thick skulls, still roamed the land. Other plant-eaters included the hadrosaurs, Edmontosaurus and Saurus, and small herbivores like Thescelosaurus. Armored dinosaurs, including Ankylosaurus, Nodosaurus, Denvosaurus, and Edmontonia, were also present. The predator species of the Maastrichtian were just as varied, with the mighty Tyrannosaurus rex leading the way as one of the top predators. Other carnivores included the smaller Tyrannosaur Nanotyrannus, the swift and bird-like Dromaeus and Romus, and the mysterious oviraptorids like Anzu. Also present were the intelligent bird-like troodontids, such as Troodon, the small Coelurosaur Richardoestesia, and raptors like Achiroraptor and Dakotaraptor. The only known dinosaur fossil ever found in Central America is a single thigh bone, femur, discovered in the middle of Honduras in an area called Comayagua Department. This discovery dates back to January 1971, when two scientists, Bruce Simonson and Gregory Horn, made the find. After the fossil was unearthed, it was sent to the National Museum of Natural History in the United States, where it was catalogued under the number USNM PAL 181339. However, it wasn't until 1994 that the fossil was formally studied and identified. It was determined to be the femur of a small, plant-eating dinosaur, likely a type of hadrosaur, which is a member of a family of herbivorous dinosaurs known for their duck-billed appearance. The very first mention of a dinosaur in Central America came earlier, in August of 1933. A Canadian newspaper, the Montreal Gazette, published an article about it, which other American newspapers also picked up. This report was about a different fossil, a metatarsus, a bone from the foot, that had been found by an explorer named George Mason. Mason was from the University of Pennsylvania and had discovered the fossil in the forest near the town of Olanchito, Honduras. According to the report, locals had also found a vertebra nearby. Unfortunately, these bones were lost over time, and because they were never studied properly, it's impossible to know for sure what type of dinosaur they belonged to. The Cambrian period, the first chapter of the Paleozoic era and the Phanerozoic eon, lasted an incredible 53.4 million years. It started about 538.8 million years ago, when the Ordovician period began. During this time, most of the Earth's land masses were located in the southern hemisphere, surrounded by the huge Panthalassa Ocean. The formation of the supercontinent Gondwana, which occurred at the end of the Ediacaran and into the early Cambrian, led to the creation of new plate boundaries. This tectonic activity, along with volcanic processes along the continent's edges, helped raise global temperatures. The climate of the Cambrian was marked by what we now call greenhouse conditions. There were high levels of carbon dioxide in the atmosphere, but oxygen levels were low, both in the air and the seas. This created a changing environment where oxygen-deprived deep ocean waters would sometimes rise to the surface, causing extinction events. However, when oxygen levels increased, life thrived, leading to bursts of new species. The Cambrian period was a time of major change for life on Earth. Before it began, most life forms were tiny, single-celled organisms that didn't leave much evidence behind. While more complex multi-celled organisms had appeared in the Ediacaran, it was the Cambrian that truly sparked a huge burst of life. This event, known as the Cambrian explosion, led to the appearance of most of the major animal groups we recognize today. It's also notable for the high number of Lagerstätte deposits, places where fossils are very well preserved. These sites captured not only the hard shells of creatures, but also the softer, more delicate parts of their bodies, offering us a rare look into the ancient past. By the end of the Cambrian, life was starting to move onto land. The first myriapods, millipedes and centipedes, arachnids, spiders and scorpions, and hexapods, insects, began to adapt to life on solid ground. Along with them, the very first plants started to take root, setting the stage for the colonization of land in the following periods. The Cambrian period was once thought to begin with the first appearance of complex life, symbolized by trilobites. However, the discovery of smaller shelled fossils that came before trilobites, along with the much earlier Ediacaran life forms, has led scientists to call for a more exact definition of when the Cambrian started. Although it had long been recognized that Cambrian rocks were different from those of the older Precambrian and the younger Ordovician periods, the Cambrian period wasn't officially confirmed until 1994, after many years of careful study. A location at Fortune Head, Newfoundland, was chosen as the formal starting point for the Cambrian period. This spot was linked to the first appearance of a fossil called Treptichnus pedum, which was then used to define the beginning of the Cambrian period worldwide. Later, scientists found this fossil just a few meters below the previously defined boundary, leading to a more refined understanding. Now, it is the Treptichnus fossil that serves as the official marker for the start of the Cambrian period. This formal recognition allowed scientists to use radiometric dating to establish dates for the base of the Cambrian across the globe. An initial estimate of around 570 million years ago became popular. However, the methods used to calculate this were later found to be inaccurate. Modern radiometric dating now provides a more exact date of 538.8 million years ago, which comes from volcanic ash in Oman and matches a significant drop in carbon-13 levels, a global pattern seen in other parts of the world. It also marks the disappearance of certain Ediacaran fossils like Namacalathus and Claudina. However, some scientists argue that the ash layer in Oman might not mark the true boundary between the Ediacaran and Cambrian periods. Instead, it could signal a change in the environment from marine to saltier, evaporate-rich conditions, suggesting that other dates ranging from 544 to 542 million years ago may be more accurate. The official point marking the boundary between the Cambrian and Ordovician periods is located at Green Point in western Newfoundland, Canada. This boundary is dated to around 485.4 million years ago. It is identified by the first appearance of a tiny marine creature called Iapetus fluvivagus, a type of conodont. In places where these conodonts are not found, scientists can use the appearance of specific planktonic graptolites or the trilobite Jujujaspis borealis to mark the boundary instead. This shift also coincides with the peak of a significant rise in carbon isotopes during that time, along with a global rise in sea levels known as a marine transgression. Some of the most notable meteorite impact sites from this time include several craters that formed in the early Cambrian period around 535 million years ago. One of these is the Nogrund crater in the Gulf of Finland near Estonia. It's a large impact crater, about 20 kilometers wide, with two smaller inner ridges and an outer ridge, all created when a 1 kilometer wide asteroid struck the Earth. Another important site is the Gardnos crater in Buskerud, Norway, which is about 5 kilometers in diameter. This crater formed around 500 million years ago in a shallow sea, and after the impact, rock avalanches and debris flows filled the area as the crater's rim collapsed. Other significant craters include the 24 kilometers wide Presqu'île crater in Quebec, Canada, the 19 kilometers wide Glion crater in Western Australia, the 5 kilometers wide Misery crater in Lithuania, and the Newport structure in North Dakota, USA, which is about 3.2 kilometers across. These craters are all thought to be around 500 million years old, or possibly a bit younger. The Cambrian explosion was a time of rapid growth and development for multicellular life. Most animals during this period lived in the water. It was once believed that trilobites were the dominant creatures of the Cambrian, but this idea turned out to be incorrect. While trilobites were present, the true rulers of the ocean were arthropods. Trilobites were only a small part of the many types of arthropods that existed. What made trilobites seem so abundant was their tough outer shells made of calcium carbonate, which fossilized more easily than the softer shells of other arthropods, leaving behind many preserved remains for scientists to discover. This period marked a huge change in the Earth's life forms. At the start of the Cambrian, most of the creatures from the earlier Ediacaran period became extinct. This extinction coincided with a sudden increase in the number of animals that burrow into the ground. The rise in burrowing animals had a lasting effect on the seafloor. Before the Cambrian, the ocean floor was covered in microbial mats, but as more animals began burrowing, they disturbed these mats, causing many species that depended on them to vanish. At the same time, other species adapted to the changing environment, creating new ecological roles. During this time, many animals that had hard, mineralized bodies began to appear, such as the bryozoans, which were once thought to have evolved much later. However, these early forms were not the fully developed versions we recognize today. Since animals with hard skeletons usually lived on the seafloor, they might not represent the larger numbers of creatures without mineralized bodies that lived in the ocean. The Cambrian explosion, marked by this sudden diversity of life, didn't last forever. Later in the period, biodiversity dropped sharply. Around 515.5 million years ago, more species began to go extinct than new ones appeared. By 5 million years later, the number of different genera had fallen from a peak of around 600 to just 450. Speciation, or the formation of new species, slowed down, with rates dropping to as low as a fifth to a third of earlier levels. Around 500 million years ago, oxygen levels in the oceans dropped dramatically, leading to low oxygen areas, while toxic hydrogen sulfide levels rose, causing another wave of extinction. The second half of the Cambrian period was surprisingly empty, showing signs of several rapid extinction events. The stromatolites, which had once been replaced by reef-building sponges, made a return as the sponges went extinct. This trend of decline continued until the Great Ordovician biodiversification event. Some Cambrian creatures made their way onto land, leaving behind trace fossils such as protishnites and climactic knights. Fossils suggest that some of the Protishnites tracks were made by euthycarcinoids, an extinct group of arthropods. The creator of the climactic Knights tracks remains unknown, but the fossil evidence suggests it could have been a large slug-like mollusk. Compared to later periods, the Cambrian period had fewer free-floating organisms. Most life forms lived on or near the ocean floor, and animals with mineralized skeletons were less common due to the ocean's chemistry at the time. The Cambrian period is also known for the unique ways it preserved life. Some fossils, like those found in the Lagerstätte deposits, even preserve soft body parts. These early ecosystems, thriving in what is now North America, would eventually pave the way for the rich diversity of plants and animals that would populate the land millions of years later. The Ordovician period, a long period in Earth's history stretching across 41.6 million years, came after the Cambrian period, starting around 485.4 million years ago and ending 443.8 million years ago when the Silurian period began. This era is the second of 6 periods in the Paleozoic era, which is a part of the larger Phanerozoic eon, a time when most of the Earth's life forms began to evolve and thrive. The name Ordovician comes from an ancient Welsh tribe, the Ordovices. It was first defined by a scientist named Charles Lapworth in 1879. He gave it this name to settle a disagreement between two other scientists, Adam Sedgwick and Roderick Murchison. They were both claiming that some rock layers in North Wales should belong to different periods, the Cambrian or the Silurian, but Lapworth found that the fossils in these rocks were unlike those found in either of those periods. He suggested that these rocks belonged to a completely new period, which later became known as the Ordovician. It wasn't until 1960, long after Lapworth's death, that this period was officially recognized by the International Geological Congress. During the Ordovician, life continued to flourish, just as it had in the Cambrian. However, the end of the period saw a dramatic extinction event known as the Ordovician-Silurian extinction, which wiped out many species in the oceans. Invertebrates like mollusks and arthropods were the dominant life forms. Arthropods, the ancestors of insects and other land-dwelling creatures, began to venture onto land during this time. By the Devonian period, they had fully established themselves on land. The first plants to live on land also appeared during the Ordovician, marking an important milestone in the evolution of life on Earth. One of the most remarkable events of the Ordovician was the Great Ordovician Biodiversification event, which greatly increased the variety of life on Earth. Fish, which were the first true vertebrates, continued to evolve, and some of them may have developed jaws late in the period. During this time, Earth was also bombarded by an unusually large number of meteorites, with up to 100 times more meteorite strikes each year than we experience today. This event, known as the Ordovician meteor event, may have been caused by a ring system around Earth at that time. During the Ordovician period, the southern continents were connected to form a supercontinent called Gondwana, stretching from just north of the equator to the South Pole. At the same time, the Panthalassic Ocean, which covered much of the northern hemisphere, stretched across more than half of the Earth. In the early stages of the Ordovician, the continents of Laurentia, now North America, Siberia, and Baltica, now Northern Europe, were far apart from Gondwana, separated by more than 5,000 kilometers of ocean. These separate continents had enough space between them to develop their unique ecosystems, especially in the deep ocean, where bottom-dwelling organisms thrived. Avalonia, a small landmass that had recently split from Gondwana, started moving northward towards Baltica and Laurentia. As this happened, a new ocean called the Archaic Ocean formed between Gondwana and Avalonia. Towards the end of the Ordovician, Avalonia collided with Baltica. Other seas and oceans also existed, such as the Tornquist Sea, which separated Avalonia from Baltica, and the Iapetus Ocean, which lay between Baltica and Siberia. Another oceanic area between Siberia, Baltica, and Gondwana eventually expanded to become the Paleo-Asian Ocean. Much later, during the Carboniferous period, the Mongol-Okhotsk Ocean formed a deep basin between Siberia and the central Mongolian regions, while much of Central Asia was part of an equatorial chain of islands, though its exact shape is still unclear. This was a time of active geological events, including frequent shifts in the Earth's plates and volcanic eruptions. However, the formation of mountain ranges wasn't mainly caused by large landmasses crashing into each other. Instead, mountains formed along the edges of continents where smaller landmasses, known as arc terrains or ribbon microcontinents, were added to the larger continents. This process involved the gradual gathering of new crust at certain continental edges. On Laurentia's Iapetus margin, new crust was added, but in other areas, the Earth's crust was stretching in some regions while compressing in others. This caused periods of both breaking apart and coming together, signaling a global change in tectonic plate movements, especially with the joining of Gondwana. One of the key events during this period was the tectonic orogeny, a major mountain-building event that began during the Cambrian period. This continued into the Ordovician, when at least two volcanic island chains collided with Laurentia to form what would become the Appalachian Mountains. While Laurentia itself remained mostly stable, other regions experienced their geological changes. A major volcanic eruption occurred around 454 million years ago, producing the largest ashfall in the last 590 million years. The eruption released up to 1,140 cubic kilometers of ash. Surprisingly, despite its size, this event seems to have had little effect on life at the time. Geological activity along the northwest edge of Gondwana, especially in what is now Spain, was also intense around 478 million years ago, during the Florian stage of the Ordovician. This activity stretched to Turkey by the end of the period. On the opposite side of Gondwana, in Australia, island arcs collided with the continent, causing the Benambran orogeny in the eastern part of the landmass. Similarly, subduction along what is now Argentina led to the Famattinian orogeny around 450 million years ago, which involved significant stretching of the Earth's crust. Meanwhile, the interior of Gondwana remained mostly geologically quiet until the Triassic period. As the Ordovician came to a close, Gondwana began moving southward, crossing over the South Pole. This shift contributed to the Hernantian glaciation, a period of intense ice ages, and was linked to an extinction event. During the Middle Ordovician, around 467.7 million years ago, a meteor shower possibly occurred, believed to have been caused by the breakup of the L chondrite parent body. While this event was not linked to any major extinction, recent studies in 2024 found that craters from this event were concentrated in a distinct band around the Earth. This suggests that the debris from the shattered parent body may have formed a temporary ring system around the planet, with meteors constantly bombarding the Earth for about 40 million years, creating these craters. During much of the late Ordovician period, life flourished in Earth's oceans, teeming with a wide variety of species. However, toward the end of this era, a series of catastrophic extinction events struck, devastating many life forms. Among the hardest hit were the conodonts and planktonic organisms like graptolites. Some trilobite groups, including Agnostida and Tychoparieida, vanished entirely, while others, such as the Asaphida trilobites, suffered significant declines. Other marine creatures, such as brachiopods, bryozoans, and echinoderms, also faced severe losses, and the endokeratid nautiloids disappeared altogether, though a few may have clung on into the early Silurian. These extinction events, known as the Ordovician-Silurian extinction, are believed to have been triggered by a dramatic shift in climate at the end of the Ordovician, likely caused by an ice age. This chilling period, which marks one of the coldest times in Earth's history over the past 600 million years, would have severely altered the global ecosystem. This mass extinction ranks as the second largest in Earth's history in terms of the proportion of genera lost, surpassed only by the Permian-Triassic extinction. The events unfolded between 447 and 444 million years ago, signaling the end of the Ordovician and the start of the Silurian period. At this time, all complex multicellular life existed in the oceans, and nearly half of all genera vanished forever. Groups such as brachiopods, bryozoans, and numerous families of trilobites, conodonts, and graptolites were hit especially hard. The most widely accepted explanation for these extinctions is the sudden onset of a cold spell near the end of the Cretaceous stage, followed by an ice age during the Hernantian stage. This abrupt cooling disrupted the warm climate that had characterized much of the Ordovician. The ice age itself was likely brief, lasting just 0.5 to 1.5 million years, as indicated by oxygen isotopes found in fossilized brachiopods. It is believed that the climate didn't return to more temperate conditions until the late Silurian. Before the Ice Age, the Earth's atmosphere experienced a significant drop in carbon dioxide levels from 7,000 ppm to 4,400 ppm. This reduction may have been driven by volcanic activity, which created new silicate rocks that absorbed CO2 as they weathered. Another contributing factor could have been the appearance of the first land plants, such as bryophytes and lichens, which likely accelerated the weathering process, further drawing CO2 from the atmosphere. This dramatic decrease in CO2 had a profound effect on the shallow seas, where most marine life thrived. Some scientists even speculate that a meteor impact occurring around the same time, along with the formation of an Ordovician ring system, may have exacerbated the cooling. As the southern supercontinent Gondwana drifted over the South Pole, ice caps began to form. Evidence of this glaciation can be found in upper Ordovician rock layers in regions like North Africa and parts of northeastern South America, which were located near the South Pole at that time. The growing glaciers caused sea levels to drop, submerging the warm, shallow seas that had once covered much of the continents. With the retreat of these seas, many vital habitats were lost, and a large portion of marine life was wiped out. When the seas eventually returned, they brought with them a dramatically reduced number of species, as many families of organisms had been decimated. Each successive glacial wave further diminished biodiversity, particularly affecting species confined to specific seas. Tropical species suffered most during the first wave of glaciation, while cooler water species were hit hardest during the second wave. However, some species were able to adapt to the changing conditions and survived, occupying the ecological niches left vacant by those that perished. Evidence from this time suggests that as the Ice Age progressed, the oceans became more oxygen-rich, creating favorable conditions for a different set of deep-sea organisms, known as the Hernantian fauna, to thrive. These species spread across most latitudes, marking a unique moment in Earth's biological history. As the glaciers eventually melted, sea levels rose, and the oceans began to stabilize. This change allowed life to slowly recover, especially with the reflooding of the continental shelves at the beginning of the Silurian. This led to a remarkable burst of biodiversity, as surviving groups of organisms began to proliferate again. Some species that had disappeared during the extinctions, referred to as Lazarus taxa, reappeared in the Silurian, suggesting they had survived in small, isolated refugia and slowly recolonized the Earth. The Silurian period, lasting about 24.6 million years, stretched from the end of the Ordovician, roughly 443.8 to 419.2 million years ago. It was the third and shortest period of the Paleozoic era and the third of 12 periods in the Phanerozoic eon. While geologists have identified the rock layers marking the beginning and end of the Silurian, the exact dates are uncertain. With a few million years of variation, the Silurian starting point is linked to a series of mass extinction events at the end of the Ordovician, when up to 60% of marine species were wiped out. One of the most significant events during this period was the rise of life on land, known as the Silurian-Devonian terrestrial revolution. This marked the first appearance of vascular plants, more advanced than earlier land plants, and the spread of fungi, including diarrhean fungi and glomamotan fungi. Three groups of arthropods, myriapods, millipedes and centipedes, arachnids, spiders and scorpions, and hexapods, insects, also made the transition to fully land-based life. Another key development during the Silurian was the evolution of jawed fish. These included placoderms, acanthodians, the ancestors of cartilaginous fish, and osteichthyons, bony fish, which later split into lobe-finned and ray-finned fish. This was a time when jawless fish, like conodonts and ostracoderms, began to decline sharply. The Silurian period was first recognized by Scottish geologist Roderick Murchison in the early 1830s. He made this discovery while studying fossil-rich sedimentary rocks in South Wales and named the period after the ancient Celtic tribe of Wales, the Silures. His friend Adam Sedgwick had already named the Cambrian period after Wales, and Murchison followed suit, although the actual location of the Silures territory didn't match the Silurian rock beds. Murchison believed the region around Kington and Woolhope Edge in Wales was significant for the period. If not, there were plenty of Silurian rocks elsewhere to justify the name. In 1835, Murchison and Sedgwick jointly published a paper titled On the Silurian and Cambrian Systems, which helped lay the groundwork for the modern geological timescale. However, disagreements arose when Murchison's Silurian rocks seemed to overlap with Sedgwick's Cambrian sequence, leading to a rift between the two friends. The conflict was eventually resolved by English geologist Charles Lapworth, who introduced a new Ordovician system, placing the disputed rocks in it. Another proposed name for the Silurian was Gotlandian, based on strata found on the island of Gotland in the Baltic Sea. French geologist Joachim Barrande expanded on Murchison's work and applied the term Silurian to a broader range of rock formations than originally recognized. He divided Silurian rocks in Bohemia into 8 stages. However, his classification was later questioned by Edward Forbes in 1854, and it was later shown that some of Barrande's stages were part of the Devonian period. Despite these revisions, Barrande's work established Bohemia as a key location for studying early Silurian fossils. During the time of the supercontinent Gondwana, it stretched across the equator and much of the southern half of the Earth. Most of the northern half was covered by a vast ocean. The sea levels during the Silurian period were high, and because the land was mostly flat with few large mountain ranges, many islands formed, creating a wide variety of environments and habitats. As the Silurian period went on, Gondwana slowly moved southward toward the colder regions of the planet. However, the ice caps during this time were not as large as those from the previous glaciation in the Ordovician period. Throughout the Silurian, the southern continents stayed together. When the ice caps and glaciers began to melt, the sea levels rose, leaving behind evidence in the form of sediments from the Silurian period that sit on top of the eroded remnants of older Ordovician rocks. This formed what geologists call an unconformity. The continents that would later form part of Europe and North America, called Avalonia, Baltica, and Laurentia, drifted toward each other, eventually forming the beginnings of a new supercontinent known as Euramerica. As the landmasses collided, the impact caused the coastal sediments that had been building up for millions of years to fold. This collision created the Caledonian mountain range, stretching from present-day New York across what is now Europe and Greenland to Norway. At the end of the Silurian, the sea levels began to drop again, leaving behind large salt deposits in areas such as Michigan and West Virginia. The newly formed mountain ranges were quickly worn down by erosion, and rivers, like the Tees River, cut through the land, eroding older rocks and forming new layers of Silurian deposits in Ohio and Indiana. During this time, the Earth was mostly covered by the Panthalassic Ocean in the northern hemisphere, while other smaller oceans, such as the Tethys and the Iapetus Oceans, existed. The Tethys Ocean, in particular, had different phases, called Prototethys and Paleotethys. The Iapetus Ocean was a narrow stretch of water between the Avalonia and Laurentia continents, while the newly formed Ural Ocean was just beginning to appear. For many years, scientists believed the Silurian period was a time of stable, warm temperatures, a sharp contrast to the extreme ice ages of the Ordovician and the scorching heat of the Devonian that followed. However, it's now known that the climate during the Silurian fluctuated dramatically. Evidence of these climate changes is found in isotopic patterns in the rock record. Sea levels rose significantly in the first half of the Silurian period and then began to fall, but there were many smaller shifts within that trend. Researchers have identified 15 times during this period when the sea levels were higher than the continental shelf, with the higher sea levels reaching about 140 meters above the lowest point. This time in Earth's history marked the beginning of a warmer greenhouse phase, where high levels of CO2 helped warm the planet. Shallow seas covered much of the equator early in the Silurian. Glaciers at the South Pole started to melt, nearly disappearing by the middle of the period. Evidence of intense storms driven by the warm seas can be found in layers of broken seashells known as coquina. The Devonian period was a time in Earth's history that lasted 60.3 million years, from about 419.2 million years ago to 358.9 million years ago. The first significant spread of plants that could reproduce without water happened, with land plants like ferns growing across the continent. These plants helped create dense coal forests that spread far and wide. By the middle of the Devonian, many plants had developed true roots and leaves, and by the end of the period, the first seed-bearing plants appeared. This change, which began in the previous Silurian period, is known as the Silurian-Devonian terrestrial revolution. The first land animals, mostly arthropods such as millipedes, spiders, and insects, also began to thrive after first arriving on land much earlier during the Ordovician period. The oceans during this time were dominated by jawed fish, especially placoderms, which became the most common type of fish in almost every aquatic environment. The Devonian is sometimes called the Age of Fishes because of this. The oceans also saw the rise of early sharks, which became more abundant than they had been in earlier periods. Meanwhile, fish that were closely related to the ancestors of all land-dwelling vertebrates began to evolve. These fish had strong fins that slowly transformed into limbs, setting the stage for the eventual movement of life onto land, although these changes would not fully happen until much later in the Carboniferous period. The first ammonites, a type of squid-like mollusk, appeared in the Devonian, and the seas were still teeming with trilobites, brachiopods, and large coral reefs. However, toward the end of the period, a major extinction event took place around 375 million years ago, wiping out many marine species. This event killed off most coral reefs, jawless fish, half of all placoderms, and nearly all trilobites, leaving only a few species behind. Another extinction event occurred around 359 million years ago, finishing off the last of the coral reefs and placoderms. Geographically, the Devonian world was dominated by the supercontinent Gondwana in the south, the small continent of Siberia in the north, and Laurussia, a medium-sized continent in the east. During this time, several major geological events took place. There were also large mountain-building events as La Russia and Gondwana collided. These included the Akkadian orogeny in North America and the beginning of the Variscan orogeny in Europe. These early collisions would eventually lead to the formation of the supercontinent Pangaea in the late Paleozoic. For a long time, the Devonian was thought to be a greenhouse age, meaning it was believed to have been a time of uniformly warm, tropical climates. This view was based on the fossils found in Western Europe and Eastern North America, regions that, during the Devonian, were near the equator as part of the supercontinent Euramerica, where signs of tropical reefs were common. However, the climate of the Devonian was much more varied than this label suggests. For example, the early Devonians saw dry conditions in many parts of the world, including Siberia, Australia, North America, and China. In contrast, Africa and South America had a warm, temperate climate. As the Devonian progressed, conditions shifted, and by the late Devonian, dry climates were less common, and temperate climates became more widespread. The Devonian period is divided into three main sections: early, middle, and late. The rocks from these periods are referred to as the lower, middle, and upper parts of the Devonian system. The late Devonian extinction wasn't just one event, but a series of extinction waves that took place at different times during the transitions between the Givetian and Frasnian periods, the Frasnian and Furmenian periods, and the Devonian and Carboniferous periods. Together, these events are considered part of the Big Five mass extinctions in Earth's history, which were some of the most catastrophic events that reshaped life on our planet. The Devonian extinction primarily impacted marine life, especially in warm, shallow waters, leaving cooler waters largely unaffected. The creatures that suffered the most were those that built the massive reef systems of the Devonian period, such as coral-like organisms. Other marine groups like brachiopods, trilobites, ammonites, and acanthodians also faced massive losses. It's estimated that up to 96% of vertebrate species, including conodonts, early jawless vertebrates, and bony fishes, disappeared during this time, along with all ostracoderms, ancient armored fish, and placoderms, early jawed fish. On land, however, the extinction event had much less of an impact. Plants and freshwater species, including the early ancestors of land-dwelling animals, tetrapods, were mostly unaffected, though some argue that the extinction may have come close to wiping out these early vertebrates. The cause of the late Devonian extinction remains a mystery, and scientists can only speculate about what triggered it. The Carboniferous period, which lasted about 60 million years, was an amazing chapter in Earth's history. It started about 359 million years ago, after the Devonian period, and ended 299 million years ago, leading into the Permian period. This period was part of the Paleozoic era and was the second to last period of that time. Interestingly, in North America, scientists often divide the Carboniferous into two smaller periods, the earlier Mississippian and the later Pennsylvanian. During this time, life on land flourished. Plants and animals were well established, and the Earth had many swamps and forests that eventually became the large coal deposits we use today. The name Carboniferous actually means coal-bearing. It was also a time of remarkable changes in life. Four-limbed animals, called stegocephalians, which evolved from fish with thick fins during the Devonian period, developed 5 fingers or toes, a feature called pentadactyly. This period is often called the Age of Amphibians, because early amphibians like temnospondyls were the main animals on land. Near the end of the Carboniferous, the first amniotes appeared, which was a big step in evolution. Amniotes were the early ancestors of both mammals and reptiles, including groups like synapsids, leading to mammals, and sauropsids, leading to reptiles and birds. Insects and other land creatures also thrived during this time. Giant creatures like Arthropleura, a millipede-like animal, and Pulmonoscorpius, a huge scorpion, roamed the land. Flying insects also appeared for the first time, adding to the variety of life in Carboniferous ecosystems. Toward the end of the period, Earth's environment changed greatly. The continents began to merge, eventually forming the supercontinent Pangaea. This caused large mountain-building events and a worldwide drop in sea levels. Climate changes led to ice ages and the destruction of the vast Carboniferous rainforests. This extinction event caused by these changes had a big effect on life in the seas and on land. One especially interesting thing about the Carboniferous period was the atmosphere. Oxygen levels changed a lot, starting low but eventually rising to around 25 to 30%, much higher than today. This high oxygen level likely allowed many insects and land creatures to grow to very large sizes. The Carboniferous period was an exciting time when Earth's plant and animal life grew and changed in new and impressive ways. On land, plants were growing in ways that had started in the late Devonian, but new types also began to appear, marking a time of plant development. Some of the main plants were horsetails, equisetaales, scrambling plants, sphenops, club mosses, lycopodiales, scale trees, lepidodendrales, and ferns, filicales. There were also seed ferns like medullosales, an early type of gymnosperm, and corditales, which were tall trees related to cycads and conifers. These plants dominated much of the Carboniferous landscape, but by the later part of the period, newer groups such as tychospermatophytes, more seed ferns, cycads, and early conifer voles began to appear. One of the most interesting plant groups was the lepidodendrales, especially the lepidodendrids. These were not small plants like today's club mosses, but giant trees that could grow up to 30 meters tall with trunks as thick as 1.5 meters. Among them were species like Lepidodendron, Anabathra, Lepidophlorios, and Sigillaria. Their roots, known as stigmaria, were also unique. Unlike modern trees, their growth and strength came from the outer layers, the cortex, rather than the inner xylem. Another important group, the Cladoxylopsids, were the ancestors of ferns and also grew into large trees, first appearing during this period. Ferns of the Carboniferous look so much like modern ferns that their fronds are almost identical to those of living species. Some may have been epiphytes, growing on other plants for support. Fossil examples of ferns and seed ferns include Pecopteris, Neuropteris, and Allothopteris, while tree ferns such as Megaphyton and Chiropteris were common. The equisetaales, or horsetails, included towering forms like calamites, which could grow as tall as 20 meters, with trunks up to 60 centimeters thick. Another plant, Sphenophyllum, was a delicate, climbing species with spiral arrangements of leaves, likely related to both the calamites and the lycopods. The corditales were particularly striking, featuring tall trees with long, strap-like leaves that could reach heights of over 30 meters. Their catkin-like structures, which carried seeds, were called cardioecarpus, and these trees thrived in swampy areas. Later in the Carboniferous, true conifers like Walchia appeared, favoring higher, drier ground. In the oceans, marine life was also varied and abundant. Groups like foraminifera, corals, bryozoans, brachiopods, ammonoids, and echinoids flourished. Brachiopods and a specific type of foraminifera called fusulinids became especially widespread during a major evolutionary event known as the Carboniferous Early Permian Biodiversification Event. Foraminifera, tiny organisms that built intricate shells, became important players in marine ecosystems. Fossilized examples like Fusulina, Alvinia, and Sacamina are still studied today. This period also saw the appearance of the first true preapulid worms, adding yet another layer of complexity to the ancient seas. The tiny shells of radiolarians, a type of plankton, can be found in chert rock formations, dating back to this period in places like Devon and Cornwall, as well as in Russia, Germany, and other parts of the world. Sponges, identified by their spicule skeletal elements and anchor ropes, appeared in various forms, including the Calispongia species, Tiliscus, and Gertiocoelia, the demosponge Chatetis, and the unique colonial glass sponge Titusvilla also thrived. Both reef-building and solitary corals thrived and grew in variety, including rugose corals like Caninia, Corinia, and Neozophrentis, as well as heterocorals and tabulate forms such as Cladoconus and Michelinaria. The conulariids, another group of corals, were also prominent, particularly represented by Conularia. Bryozoans, or moss animals, were widespread in some areas, with types like Phenostella, Polypora, and Archimedes, named for their resemblance to an Archimedean screw, being particularly abundant. Brachiopods, a group of marine animals resembling clams, also flourished, with some, like the Gigantoproductus, growing as large as 30 cm wide and possessing incredibly thick shells. Other brachiopods, such as Chatetis, were smaller and simpler in shape. Species from the groups Atheridida, Spiriferida, Rhynchonellida, and Terebratulida were also common, along with inarticulate forms like Dicinisca and Crania. Many species had wide-ranging distributions, showing only slight variations across different regions. Annelid worms, such as cololites, were commonly found in certain rock layers. Among mollusks, bivalves continued to grow in both number and importance. Notable genera from this time include Aviculopecten, Posidonia, Nucula, Carbonicola, Edmondia, and Modiola. And gastropods, or snails, were numerous as well, with examples like Murchisonia, Euomphalus, and Naticopsis. Nautiloid cephalopods, like the nautilus, appeared with tightly coiled shells, while straight-shelled and curved-shelled varieties became increasingly rare. Ammonoids, such as Enigmac-eras, with their spiral shells, were common during this period. Trilobites, once abundant, were becoming rarer and were now mainly represented by the proetid group. Ostracods, small crustaceans that lived in the sea, were abundant and formed a major part of the Meobentos, tiny organisms in marine and freshwater environments. Common genera of ostracods included Echmina, Baedia, and Kona. Crinoids, a type of marine animal with a stalk, were plentiful, though their diversity began to decline in the Middle Mississippian. They formed dense underwater forests in shallow seas, and their remains formed thick rock layers. Important crinoid genera included Actinocrinus, Woodocrinus, and Acinocrinus. Sea urchins, or echinoids, such as Archaeosideris and Periscodomus, were also present. Blastoids, another group related to crinoids, reached their peak during this time. Fossilized remains of air-breathing insects, millipedes, and arachnids, such as spiders and scorpions, have been discovered from the Carboniferous period, though they were not as common as marine species. These arthropods were numerous and well-developed when they did appear. Some grew to extraordinary sizes, like the millipede Arthropleura, which could reach lengths of 2.6 meters, making it the largest land invertebrate known. Among the insects, the predatory griffin flies, Protodonata, were especially remarkable, with species like Meganeura, a giant dragonfly having a wingspan of up to 75 centimeters, the largest flying insect ever recorded. Other notable groups included relatives of modern-day mayflies, the sap-sucking Paleodictyoptera, herbivorous Protorthoptera, and early cockroach ancestors, Dictyoptera. Many insect fossils have been found in coal fields in places like Saarbrücken and Coventry, as well as in hollow tree trunks in Nova Scotia. British coal fields have also yielded preserved insects, such as Archopolis from Derbyshire, which had large wings with traces of brilliant colors. In the tree trunks of Nova Scotia, land snails like Archaeozonites and Dendropupa have been discovered. By the middle of the Carboniferous, amphibians were diverse and widespread, some growing as large as 6 meters long. Many of these amphibians were fully terrestrial and had scaly skin, while others remained aquatic. Among the largest amphibians were early tetrapods grouped under Labyrinthodontia, with long bodies, bony plates on their heads, and underdeveloped limbs. These creatures, some reaching over 2 meters, were joined by smaller amphibians of the Lepospondyle group, often measuring only 15 centimeters. Some amphibians, like Loxoma and Eogyrinus, lived in rivers, while others, such as Ophiderpeton and Hyloplesion, may have been semi-aquatic, and species like Dendropeton and Tersomius were fully terrestrial. The decline of the Carboniferous rainforest, caused by cooler and drier conditions, slowed the evolution of amphibians, which struggled to adapt. In contrast, amniotes, creatures capable of laying eggs on land, thrived. The amniote egg was one of the period's greatest evolutionary advancements, allowing species to reproduce outside of water. Amniotes also developed scales and claws, which helped them adapt to land life. This marked the rise of early reptiles like Hylonomus and the first known synapsids like Archaeopteryx. These synapsids rapidly diversified, becoming dominant in the Permian, but their reign was eventually overtaken by other groups during the Mesozoic. Reptiles also diversified but remained small until the Mesozoic, when they would eventually dominate the Earth's land, seas, and skies. Reptiles experienced a major evolutionary surge in response to the drier climate before the rainforest collapse. By the end of the Carboniferous, amniotes had already branched into various groups, including early synapsid pelycosaurs, protorothyridids, and early saurians, laying the groundwork for the evolution of later, more diverse reptilian groups. The long era we call the Paleozoic came to a dramatic end during the Permian period. By then, Earth's continents had come together to form a massive supercontinent known as Pangaea, which stretched across an area of about 148 million square kilometers. The end of the Paleozoic was marked by one of the most catastrophic events in Earth's history. A global surge in volcanic activity triggered the Great Dying, the deadliest extinction event the planet has ever experienced, wiping out nearly 90% of all plant and animal species. Despite this devastation, life managed to make a final stand, producing some of the most remarkable and unique creatures the world had ever seen. One of these was the famous Dimetrodon, a large lizard-like animal known for its sail-like structure along its back. Though often mistaken for a dinosaur, Dimetrodon lived long before dinosaurs during the Permian in what is now North America. It was part of a group of animals called synapsids, which would eventually give rise to mammals, including humans. North America was home to many synapsids at the time. Dimetrodon likely hunted Diadectes, a large plant-eating creature that looked somewhat similar to it. These creatures may have used their sails to regulate body temperature, suggesting they were cold-blooded. One of the more unusual synapsids was Cassia, a creature with a massive barrel-shaped body and an oddly small head perched on top. This strange creature would have resembled a giant headless tortoise, possibly even living a semi-aquatic lifestyle in the oceans. Other familiar yet fascinating creatures were evolving. For instance, the Helicoprion, a type of shark with a unique set of spiral teeth that protruded from its lower jaw. Despite how it's often depicted, these teeth were likely far less dramatic than the wild, spiraling images you might have seen in popular illustrations. Meanwhile, the freshwater wetlands of the American Permian landscape were home to Diplocalus, an amphibian with a wide, boomerang-shaped skull that allowed it to glide smoothly through the water, propelled by its flat, paddle-like tail. During the Permian period, marine life flourished with a wide variety of creatures, including mollusks, brachiopods, and echinoderms. Brachiopods were especially diverse, with a group called Productida dominating the oceans. They made up about half of all the brachiopod species during this time and played an important role in shaping the ecosystem, especially within the coral reefs. Among the ammonoids, a group called Goniatitida was abundant during the early to middle Permian, but their numbers dwindled by the late Permian. Another group, Protrachiceratida, wasn't as diverse, but the Ceratitida emerged from it during the mid-Permian and grew significantly in number during the late Permian. Trilobites, once widespread, became rarer over time with only 3 families, Proetida, Brachymetapidae, and Philipsiidae, surviving into the Permian. These ancient creatures underwent a final period of growth before nearly disappearing by the end of the Permian. Corals also saw a drop in diversity as the period progressed. On land, life was equally diverse, with plants, fungi, arthropods, and tetrapods all thriving. However, the period was also marked by the development of vast deserts that spread across the interior of the supercontinent Pangaea. The northern hemisphere saw large deserts emerge, leaving the land barren and red from the intense heat and lack of vegetation. This shift marked the end for many older species of plants and animals, pushing them to the edges of ecosystems. At the start of the Permian, plants from the Carboniferous period, like the swamp-dwelling lycopod trees, such as Lepidodendron and Sigillaria, were still thriving. But around the middle of the Permian, these plants were gradually replaced by more advanced seed ferns and early conifers as a result of the collapse of the Carboniferous rainforests. The Permian period also saw the rise of many new groups of conifers, including the ancestors of today's tree families. In the southern hemisphere, the Glossopteris flora formed large, rich seed fern forests. This region likely had high levels of oxygen, which also supported the growth of ginkgos and cycads. Insects, which had first appeared during the Carboniferous, underwent a massive increase in variety during the early Permian. However, towards the end of the period, there was a noticeable drop in both the number of new species and the extinction rates. Insects like Paleoptera, Polyneoptera, and Paraneoptera dominated the ecosystems. Meanwhile, the Paleodictyoptera, which had been common during the Carboniferous, started to decline due to competition with Hemiptera, whose similar mouthparts allowed them to occupy the same ecological niches. Some large flying insects, like the Meganisoptera, which were the largest flying insects ever, also faded away during this time. Meanwhile, the modern insect order Holometabula, which includes butterflies, beetles, and flies, saw rapid diversification. Insects like Grilloblattodea, which are related to today's ice crawlers, reached their peak diversity during the Permian, making up as much as a third of all insects in some areas. The first Mecoptera, known as scorpion flies, appeared in the early Permian, and by the late Permian they had become widespread. Some species, such as Mesocycidae, had long proboscises, suggesting they might have helped pollinate early gymnosperms. The first beetles also appeared during the Permian, with early forms like those in the Permacupedidae family, feeding on decaying wood. Over time, certain beetle families expanded into new habitats, including aquatic environments. By the late Permian, evidence from fossils suggests that the most diverse modern beetle group, Polyphaga, had already begun to emerge. The fossil record of the Permian period is incomplete and uneven, with missing parts in certain periods. In the early Permian, fossils are mainly found in warm areas of Europe and North America, while the middle and late Permian records are more plentiful in the temperate Karoo supergroup of South Africa and the Ural region of Russia. During the early Permian, North America and Europe were home to a variety of ancient land-dwelling animals, mostly made up of early synapsids, a group of reptiles that eventually became mammals. These included plant-eating Edaphosaurus, as well as meat-eating creatures like sphenodontids, diadectids, and amphibians. Some early Permian reptiles, such as a coelus, were small insect eaters. Synapsids thrived and evolved during the Caesuralian, the earliest part of the Permian, with some species, like Dimetrodon, growing quite large. The special features of synapsids allowed them to thrive in the increasingly dry climate of the Permian, making them the dominant vertebrates. However, around the boundary between the Caesuralian and Guadalupian periods, a major change in the animal kingdom occurred. Amphibians started to decrease, and early pelycosaurs were gradually replaced by more advanced therapsids. The change from early synapsids to these new groups took a slow 20 million years, spanning from the Sackmarian to the end of the Kungurian. During this time, the interactions between predators and prey among land-dwelling synapsids became more complicated. There is some uncertainty about the timing of this change. Fossils from North America show the end of land deposition in the late Caesuralian, while records from Russia begin in the early Guadalupian. This gap in the fossil record, known as Olson's Gap, has caused debate about whether there was a global pause in the fossil record around the late Kungurian and early Rhodian, possibly pointing to a major extinction event. Some researchers believe the fossil records of North America and Russia overlap, with the latest North American fossils dating to the Rhodian. This suggests that a major extinction event, referred to as Olson's extinction, may have happened. The Middle Permian period in South Africa and Russia was dominated by therapsids, particularly a group called Dinocephalia. These creatures thrived until the end of the Middle Permian, when they were wiped out during the Capetanian mass extinction event. In the late Permian, advanced therapsids, including the predatory saber-toothed Gorgonopsians and plant-eating Dicynodon, became more common. Large, herbivorous parareptile reptiles also thrived during this time. The Archosauromorpha, the group of reptiles that would eventually give rise to dinosaurs, pterosaurs, and other reptiles, began to appear and change. This period also marked the first appearance of archosaur forms in the late Permian. The late Permian also saw the emergence of cynodonts, a group of therapsids that are ancestors of modern mammals. Another group, the Therocephalia, which included creatures like Lycaenops, appeared in the Middle Permian. There were no flying vertebrates at this time, but a lizard-like group called the Vigeltisauridae, known from the late Permian, had wings that could extend like modern gliding lizards, making them the oldest known gliding vertebrates. Permian stem amniotes, early ancestors of reptiles, included lepospondylus and batrachosaurs according to some studies, while others suggest they were only represented by diadectomorphs. The variety of temnospondyls, a type of amphibian, reached its peak in the Caesuralian, but sharply declined during the Guadalupian-Lopingian periods following the Olson-S extinction. By the end of the Permian, their numbers had dropped below those of earlier periods. Modern amphibians, or lysamphibians, are believed to have originated during the Permian, evolving from a group of disaurophoid temnospondyls, or lepospondyls. After the Great Dying, the Mesozoic era, the age of dinosaurs, truly began, but not all at once. Dinosaurs didn't appear immediately. They first emerged towards the end of the Triassic period. Before they arrived, other types of reptiles were the dominant creatures. The Triassic period began around 251 million years ago, and by then, North America was positioned on the far west side of the supercontinent Pangaea, close to what would eventually become South America and Africa. What is now the United States was still mostly covered by the massive Panthalassic Ocean, which, by the end of the period, was home to some truly remarkable creatures. One of these creatures was Shonisaurus, a giant marine reptile that grew up to 15 meters long. It swam the oceans, possibly in groups or pods, in search of food. Despite its massive size, Shonisaurus wasn't even the largest of its kind. That title went to Shastasaurus, which grew an astonishing 21 meters in length, making it one of the biggest creatures the Earth had seen at the time. These animals were the largest life forms on the planet until even bigger creatures evolved millions of years later. On land, reptiles had diversified into many fascinating forms. Trypanosaurus resembled a sloth and lived in the trees, using its long, powerful tail to help it grip the branches. Smiloseuchus, a 12-meter-long predator, prowled the wetlands, resembling a crocodile in appearance. Meanwhile, Arizonosaurus, a four-legged apex predator, hunted the deserts, looking much like earlier depictions of Spinosaurus. Reptiles had spread across the globe, and the Mesozoic era was fully underway. But despite these incredible creatures, the Triassic period is most remembered for setting the stage for the rise of the dinosaurs. In what would one day become the United States, small and unassuming theropods like Calophysis, Camptosaurus and Demonosaurus darted across the floodplains and wetlands, hunting lizards, fish and invertebrates. These dinosaurs were tiny and humble compared to the giants that would come later. The true magnitude of dinosaur evolution would only become clear as the world moved into the Jurassic and Cretaceous periods. During the Triassic period, reptiles, especially a group called archosaurs, were the dominant land vertebrates. Archosaurs included the dinosaurs, which first appeared in the late Triassic but didn't become the leading species until the Jurassic. Most of the archosaurs that thrived during this time were pseudosuchians, which were ancestors of modern crocodiles. At the same time, a new branch of archosaurs evolved the ability to fly, becoming the first vertebrates to do so, the pterosaurs. Although the therapsids, the dominant land vertebrates of the previous Permian period, showed some growth in numbers during the Triassic, they eventually declined. This included groups like the Dicynodontia and Cynodonts, which became less common as the period went on, and most of them went extinct by its end. However, the first mammals, which evolved from cynodonts, began to appear in the Triassic. These early mammals survived the mass extinction at the end of the period and would later thrive in the Jurassic. Amphibians in the Triassic were mainly represented by temnospondyls, large aquatic predators that had survived the end Permian extinction. Although they flourished briefly, they too eventually disappeared by the end of the Triassic. However, early forms of modern amphibians like frogs, salamanders and caecilians began to appear and would survive the extinction event. Meanwhile, the first modern fish species, including early holosteans and teleosts, emerged early in the Triassic. These fish quickly diversified, becoming common in both freshwater and marine environments. The vast supercontinent of Pangaea covered most of the Earth during the Triassic, but near the end of the period, Pangaea began to break apart into two smaller continents, Laurasia in the north and Gondwana in the south. The climate during the Triassic was mostly hot and dry, with large deserts covering much of Pangaea's interior. However, as the continents drifted apart, the climate became more humid. The Triassic period ended with a massive extinction event, wiping out many species, including most pseudosuchians. This event cleared the way for dinosaurs to become the dominant life forms during the Jurassic. In the oceans, new types of corals appeared in the early Triassic, creating small reefs compared to the larger reef systems of earlier periods. By the end of the Carnian stage, a reef crisis occurred in South China. New marine life also began to flourish, including species like serpulids, ammonites, and various bivalves, which quickly became abundant. The Middle Triassic saw a burst in the diversification of aquatic insects, especially those belonging to the group Holometabola, which includes most of today's modern insect species. After the mass extinction that ended the Permian period, the fish species in the Triassic were relatively uniform, with many sharing a wide global distribution. Coelacanths, a group of fish that had been around since the Devonian period, reached their peak diversity during the early Triassic. Ray-finned fish, or actinopterygians, also underwent remarkable diversification in the early Triassic, reaching their highest diversity in the Middle Triassic. This diversification is still not completely understood due to preservation biases in the fossil record. The first true teleosts, the most diverse group of fish today, appeared during this time. Large predatory fish, such as Saurichthys and Bergeria, which could grow over 3.9 feet long, appeared early in the Triassic and became widespread. Lakes and rivers were inhabited by lungfish, such as Ceratodus, which are known for their unique dental plates, which appear frequently in fossils. Hybodonts, shark-like cartilaginous fish, dominated both freshwater and marine environments throughout the period. The last of the ancient, mostly Paleozoic Eugnathus species survived into the early Triassic. Temnospondyl amphibians were another group that survived the Permian-Triassic extinction. Although once abundant on land and in water, the terrestrial species mostly went extinct during the extinction event. The survivors in the Triassic were aquatic or semi-aquatic and included species like Tupilicaris, Thusuchus, and Micropholis, which eventually went extinct in the early Triassic. However, the stereospondyls, the most successful group, continued to thrive into the Cretaceous period. Some Triassic stereospondyls, such as Mastodonsaurus, grew as large as 20 feet long, while some groups, like Trematosaurus, thrived briefly in the early Triassic. Others, like the Metoposaurus, lasted throughout the Triassic period, and some species, like Plagiosaurus, came to prominence later in the era. The first modern amphibians, or Lis amphibians, also appeared in the Triassic. The ancestors of frogs were already present in the early Triassic, but the group as a whole didn't become common until the Jurassic, when the larger temnospondyls began to disappear. In the Triassic period, most of the reptiliomorphs, ancient creatures that led to the rise of amniotes, disappeared. However, two aquatic groups survived: Embolotherium, which only lasted into the early Triassic, and the Croniosuchia, which lasted until the end of the period. The Permian-Triassic extinction had wiped out most of life on land, although surviving species slowly repopulated the Earth. The recovery was slow, and it took millions of years for life forms to return to complex ecosystems with stable food chains. After this extinction event, reptiles called archosauromorphs became more varied. These reptiles had already appeared in the Permian, but thrived after the extinction. One early group of archosauromorphs, known as Thecodontosaurus, had long lizard-like bodies and were probably a mix of different species, not one true family. Some, like Tanystropheus, developed extremely long necks, with their necks being even longer than their bodies. Others, like the Charovipterygidae, had long back legs and used them for gliding. Meanwhile, rhynchosaurs, which were thick, barrel-shaped plant-eaters, lived briefly but were once abundant in Triassic ecosystems. They used sharp beaks and multiple rows of teeth to cut plants. Another group, the Allocotosaura, resembled iguanas and included species like Trilophosaurus, Pteraterpiton, and Shringosaurus. Some of these, like Shringosaurus, grew as long as 3 to 4 meters and were horned plant-eaters. A more predatory group, called Archosauriforms, became dominant in the Triassic. These reptiles had sharp teeth and stood upright, making them excellent hunters. Some, like the Erythrosuchidae, were large-headed and strong, while others, like the phytosaurs, were long-snouted, semi-aquatic hunters that resembled modern crocodiles. However, their similarity to crocodiles is an example of convergent evolution, meaning they developed similar traits independently. By the early Triassic, true archosaurs appeared and split into two main branches. One led to birds, Avimatatosalia, and the other to crocodiles, Pseudosuchia. Early archosaurs were not very numerous, but later gave rise to the first pterosaurs and dinosaurs. Pterosaurs, which were flying reptiles, appeared in the late Triassic and spread quickly. Dinosaurs also began evolving in the Carnian stage of the Triassic, including early sauropodomorphs and theropods. While most Triassic dinosaurs were small predators, a few, like Cretaceous, were more common and grew to about 1 to 2 meters in length. Some sauropodomorphs lived in cooler areas during this time. Their echs also evidence that the large predator smock might have been an early dinosaur or a type of pseudosuchian, though it's not entirely clear. Pseudosuchians, a group of archosauriforms, were more ecologically dominant during the Triassic. They included plant eaters like Atosauria and large meat eaters like Rauisuchia. Heavily armored Atosauria lived in the late Triassic until they went extinct during the Triassic-Jurassic Extinction. They were mostly plant eaters, feeding on low-lying plants, though some may have eaten meat. Rauisuchians, which were the top predators of their time, included a variety of species such as giant hunters, smaller bipedal omnivores, and large, slow-moving creatures with sails on their backs. These predators probably filled the role later taken over by theropod dinosaurs. Some Rauisuchians eventually evolved into the first crocodilians. The seas were also full of life during the Triassic, with many different marine reptiles. These included the Sauropterygia, which had creatures like Pachypleurosaurus and Nothosaurs, and Placodonts, the first plant-eating marine reptiles. The earliest known plesiosaurs also appeared during this time. Thecodontosaurus, lizard-like reptiles, and ichthyosaurs, which looked like fish but were reptiles, also thrived in Triassic oceans. Some ichthyosaurs grew to large sizes by the Middle Triassic. On land, the first turtles, like Progonocheles and Proterocerces, appeared during the late Triassic. The Sphenodontia, part of the Lepidosauromorpha group, also first appeared in the fossil record during this time. Other reptiles, like the Procolophonidae, were small, lizard-like plant eaters, and the Drepanosaurus, which had bird-like heads and specialized claws, lived in trees. Therapsids, a group of mammal-like reptiles, survived into the Triassic, including Dicynodontia, Therocephalia, and Cynodonts. Caenognathus, a type of cynodont, was a top predator in the early Triassic, while other cynodonts and Dicynodontia were plant eaters. During the Carnian period, some advanced cynodonts evolved into the first mammals. Throughout the Triassic, archosaurs began to dominate the land, pushing therapsids into smaller nocturnal roles. This shift may have encouraged the evolution of mammals, which adapted to a nocturnal lifestyle, developing fur and a higher metabolism to survive. Some of the most remarkable fossil sites from this period include the Dianarian-aged Guangling biota and the Spartian-aged Paris biota, which offer exceptional insights into life after the Permian-Triassic extinction. The Monte San Giorgio Lagostetta in Italy and Switzerland also preserved a variety of fossils, including marine reptiles like Nusticosaurus and Tanistropheus, as well as land animals like Macrocnemius. The Jurassic period, which spanned from about 201.3 million to 145 million years ago, is most famously known for the giant dinosaurs that roamed the Earth. These massive creatures, especially in what is now North America, were some of the largest animals to ever exist. Among them were the towering Brachiosaurus and Camarasaurus, which loomed high above the ground, feeding on the treetops, while smaller creatures foraged below. With their huge teeth designed for stripping and chewing tough vegetation, these dinosaurs were well equipped to reach the branches of trees and consume vast amounts of plant material. Brachiosaurus in particular was an impressive species. It had an incredibly long neck that stretched up to 26 meters in length and reached a height of about 15 meters. Its neck was held upright, giving it a unique appearance compared to other dinosaurs. One of its most remarkable features was its legs. The front legs were much longer than the back ones, which is how the creature earned its name, which translates to arm lizard. To survive in the warm climate of the Jurassic, Brachiosaurus had air sacs in its body to help keep cool, a clever adaptation that reduced the need for constant feeding and helped the dinosaur conserve energy. Another famous dinosaur from the same time was the Diplodocus, which was quite different from Brachiosaurus. This dinosaur had a more horizontal body posture and was supported by 4 sturdy, pillar-like legs. It had an incredibly long neck and an even longer tail, which helped balance its body. While much shorter than Brachiosaurus, Diplodocus preferred to feed on lower-growing plants and was adapted for this lifestyle. Its tail was a crucial defense mechanism, capable of swinging like a whip to strike predators, such as large carnivores that roamed the region. Newborn Diplodocus were tiny, only about 1 meter long when they hatched. To protect the young from swift predators like Ornitholestes and Dilophosaurus, which could easily catch them, the eggs were hidden in nests deep within dense forests. As the young dinosaurs grew, they would eventually leave the shelter of the forests and join large herds on the open plains, where they faced new threats. One of the most dangerous predators of the time was Allosaurus, often called the Lion of the Jurassic, because it hunted in packs. These large, fearsome carnivores would gather in groups to attack sick, weak, or young dinosaurs. With their sharp claws and powerful jaws, Allosaurus would leap and slash at their prey in coordinated attacks. They weren't picky eaters either, preying on a wide range of animals, from smaller herbivores to other predators. However, some paleontologists believe that Allosaurus might have been more of a scavenger, feeding on the remains of animals killed by other predators, much like a giant vulture. The iconic Stegosaurus also roamed the Jurassic landscapes of North America, known for its distinctive spiked tail and large bony plates along its back. Stegosaurus has long been a subject of scientific debate. One prevailing theory is that the plates helped regulate the dinosaur's body temperature, much like the sail of the Dimetrodon from earlier periods. Other theories suggest that the plates were used for display, possibly to attract mates or intimidate rivals. The plates might also have been a defense against larger predators like Allosaurus and Torvosaurus, warning them not to mess with this armored dinosaur. The Jurassic period in what would become the United States was also home to many smaller herbivores, such as Dryosaurus, Othnielia, and Frutodens. These smaller dinosaurs foraged among the dense forests, contributing to the incredible diversity of life at the time. The Jurassic period was a time of big changes and adaptations for prehistoric reptiles. After the Triassic-Jurassic extinction, many ancient creatures disappeared, making space for new ones to grow. Among the survivors were crocodilomorphs, the ancestors of today's crocodiles. These reptiles first appeared in the late Triassic and were the only members of their group, the Pseudosuchians, which included crocodile-like reptiles, to survive the extinction. Other Pseudosuchians, like the plant-eating Etosauria and the meat-eating Rauisuchia, didn't make it. Crocodilomorphs quickly spread and changed during the early Jurassic. While today's crocodiles mostly live in water and hunt by ambushing their prey, their Jurassic ancestors lived in different ways. Some walked on land with long legs built for running, and others lived in the ocean. Amazingly, scientists have even found fossilized teeth in Arizona from an early plant-eating crocodilomorph, showing that some of them tried out plant-based diets, a behavior that showed up several times during the Mesozoic era. One particularly interesting group, the Thalattosuchians, adapted to life in the sea. These ocean-dwelling reptiles developed flippers instead of legs, smooth bodies and strong tails with fins to help them swim. These features allowed them to rule the Jurassic oceans as predators. Another group, the Neosuchians, started moving from land to freshwater environments, eventually evolving into crocodile-like forms more similar to those we see today. During this time, other reptiles were also thriving. The rhynchocephalians, Ancient relatives of the tuatara spread all over the world and evolved into many shapes and sizes, including aquatic, snake-like creatures with tiny limbs, plant eaters, and shell crushers. These small reptiles were very common in the Jurassic, but later disappeared from areas like Asia. Meanwhile, lizards and snakes, known as squamates, were just beginning to evolve. Early squamates lived in various habitats, and some, like the gecko-like Eichstetisaurus from Germany, were even good climbers. The Jurassic oceans were full of amazing creatures. Ichthyosaurs, sleek marine reptiles, survived a tough period after the Triassic extinction. During the early Jurassic, they thrived with species like the giant predator Temnodontosaurus and the swordfish-like Euhinosaurus. But by the Middle Jurassic, most ichthyosaurs were gone, leaving behind the adaptable ophthalmosaurids, which ruled the oceans for millions of years. Similarly, plesiosaurs, known for their long necks and flippers, became major marine predators after other groups of marine reptiles died out. Early plesiosaurs were small, but over time, some grew huge, with large heads and short necks to hunt bigger prey. Interestingly, plesiosaurs didn't just live in the ocean, they also swam in freshwater lakes and rivers. In the skies, pterosaurs, the first animals with powered flight, were evolving quickly. Early Jurassic pterosaurs, like the fish-eating Rhamphorhynchidae, did well, while later types, like Pterodactylus, developed special jaws to eat hard-shelled prey. By the end of the Jurassic, advanced pterodactyloids were flying high, with features like needle-like teeth for filter feeding or other unique diets. On land, dinosaurs were becoming the most dominant animals. Their rise happened after their competitors went extinct, and many new species appeared. Plant-eating dinosaurs, like the puzzling Chilosaurus, emerged, while theropods, the group that includes predators like Allosaurus, continued to evolve. Jurassic dinosaurs weren't just about large predators and herbivores. Smaller feathered theropods, like the bat-winged Scansoriopterygidae, were gliding through forests, giving clues about how birds first evolved. The first members of famous groups, like the tyrannosaurs and raptors, Dromaeosauridae, also appeared, paving the way for their success in the Cretaceous. The Cretaceous period stands as one of the most exciting eras in the history of dinosaurs, often considered the golden age of paleontology. This time was home to many of the most well-known and awe-inspiring dinosaurs, and it marked a pivotal moment in Earth's geological history. During this period, the land that would become North America was beginning to take shape. However, the continent wasn't whole. It was divided into two massive landmasses, Larimedia in the west and Appalachia in the east. Separating them was the Western Interior Seaway, a vast inland ocean that stretched from the Arctic Ocean in the north to the Gulf of Mexico in the south, effectively splitting the land right down the middle. This dynamic landscape was a haven for countless dinosaur species thriving in different environments across the continent. Among these ancient giants, one name stands out above all others: Tyrannosaurus rex, the undisputed king of the Cretaceous. Towering at an average length of 12 meters, Tyrannosaurus was a colossal apex predator. Its hunting grounds were teeming with potential prey, ranging from heavily armored herbivores like Ankylosaurus and Triceratops to more agile dinosaurs like Pachycephalosaurus and Hadrosaurus. However, life as a top predator was anything but easy. Prey like Ankylosaurus was no pushover. This dinosaur was essentially a walking fortress, complete with thick armor and a club tail powerful enough to shatter bones. Even Tyrannosaurus, with all its strength, risked life-threatening injuries in such encounters. Similarly, Triceratops, another Cretaceous heavyweight, posed a significant challenge. These three-horned giants could grow up to 8 meters long, and their sharp horns were formidable weapons against any predator daring to attack. Beyond Tyrannosaurus, its relatives revealed the fascinating diversity within the tyrannosaur family. One such cousin, Nanuqsaurus, lived much farther north in what is now Alaska. Unlike the warmer habitats of other tyrannosaurs, Alaska during the Cretaceous was much colder. To adapt to these icy conditions, Nanuqsaurus likely sported a covering of feathers or hair-like filaments to keep warm in the frigid climate. Meanwhile, other groups of carnivorous dinosaurs, known as theropods, were evolving into astonishing new forms across North America. Take Utahraptor, for instance, a relative of the famous Velociraptor, but significantly larger, measuring up to 6 meters long. Unlike the sleek, smaller Velociraptor, the Utahraptor was a powerful predator, using its size and sharp claws to dominate its environment. During the Cretaceous period, dinosaurs lived all over North America in an amazing variety of shapes and sizes. Take the Velociraptor, for instance. While often shown as much bigger in movies like Jurassic Park, real velociraptors were smaller and had a curved, sharp claw, similar to their bigger cousin, the Utahraptor. This dangerous hunter, which might have worked in groups, could have teamed up to bring down plant-eating giants like hadrosaurs or smaller sauropods, using the thick forests as hiding places to attack. But not all dinosaurs were scary meat-eaters. Among the thick plants lived a strange type of dinosaur called Nothronicus, a relative of the odd-looking Therizinosaurus. Unlike its meat-eating relatives, Nothronicus ate plants. It stood upright on 2 legs with a long neck that helped it reach high branches for food. Its long claws weren't for hunting, but for pulling leaves and branches closer to its mouth. These gentle giants showed a very different side of the dinosaur world. Dinosaurs, however, were only part of the lively world that existed during the Cretaceous. The skies were full of amazing flying reptiles, like the well-known pteranodon, famous for its wide wings and eye-catching head crest. Alongside it flew the unusual Nyctosaurus, with its unique head shape, and the giant Quetzalcoatlus, one of the largest flying creatures ever. These animals ruled the skies, their strange looks showing how nature could create so many different designs. Meanwhile, the Western Interior Seaway, a huge sea that cut North America in half, was packed with life. Here, the mosasaurs were the top predators, giant sea reptiles related to modern snakes and lizards. Among them was Tylosaurus, a fearsome hunter that could grow up to 13 meters long, making any swim a risky choice. But these hunters weren't alone. Massive sea turtles like Archelon also lived in these waters. Despite their size, their surprisingly light shells kept them safe from most dangers. On the seaway shores, groups of Hesperornis, flightless seabirds that looked like long, thin penguins, nested and hunted for fish. Their sharp beaks were perfect for catching the fish that filled the waters, but they had to watch out. One such fish, the 6-meter-long Xiphactinus, was a powerful predator with long, needle-sharp teeth. It could easily snatch an unwary Hesperornis right out of the water. This time in history was unmatched in its variety of life, with plants and animals evolving into some of the most incredible and strange forms ever seen on Earth. The Cretaceous period ended suddenly 66 million years ago, marking the end of one of Earth's biggest events, its 5th mass extinction. While many ideas try to explain what happened, the most popular one suggests a huge asteroid hit the Yucatan Peninsula in Mexico, with an impact stronger than millions of atomic bombs. This event wiped out the dinosaurs that hadn't already turned into birds, forcing life on Earth to start over. After this, the planet began fresh. The warm green forests of the Tertiary period began to grow, and small, simple mammals that once hid in the shadows of the dinosaurs began to rise. Over time, these early mammals started to dominate the Earth, and life slowly began to look like the world we know today. In North America, many species that would later become familiar appeared, setting the stage for the creatures that would eventually rule the planet. The Tertiary period began with the Paleocene epoch. During this time, strange creatures roamed the land, including Barylambda, an animal similar in shape to a large shrew, and Pantolambda, which, though not related, resembled the giant ground sloth that would dominate the land millions of years later. In the thick forests of the time, Synthetosaurs lived, a strange creature that looked like a mix between a rat and a dog, with long, sharp teeth. The Paleocene eventually gave way to the Eocene epoch, where life grew larger. This period saw the rise of huge plant-eaters like Uintatherium, a creature that resembled a giant rhinoceros. Its large horns stood out against the landscape. Meanwhile, stranger creatures like Stylinodon, about the size of a jaguar but resembling a wild boar, adapted to chew roots and tubers with their large, powerful teeth. Mesohippus, an early mammal with a long snout, resembled a giant anteater wandering the land in search of food. In the seas, the first whales began to evolve. Fossils of the giant Basilosaurus, a huge whale that grew to 18 meters long, have been found in the US, making it one of the largest mammals to have ever existed, an impressive size by any standard. The last part of the Tertiary period, the Oligocene epoch, brought some of the first large mammalian meat-eaters. Hyaenodon, a predator built like a modern leopard, roamed the plains, while species of hyaenodontids, strong animals with no direct modern relatives, appeared in America as well. One of the most famous animals of this time was Diodon, also known as the hell pig. Standing 2 meters tall, this hoofed mammal had long, crushing jaws, suited for eating both plants and meat. It is believed that Diodon likely used its powerful jaws in fights with rivals, but it may have also been a scavenger, possibly even hunting other predators to steal their food. By the end of the Oligocene, mammals had fully taken over the Earth, just as dinosaurs once had. North America, in particular, had become a land of amazing creatures, setting the stage for the mammals that would eventually rule the planet. If the American Tertiary period was remarkable, then the Quaternary period was truly breathtaking, even for the most seasoned paleontologists. This era marked the arrival of many animals that we recognize today. In North America, it began with the Miocene epoch, a time when vast grasslands and dense forests stretched across much of the continent. These lush environments created the ideal setting for large, powerful creatures to evolve, specially adapted to feed on the grasses that were quickly spreading across the land. As these new plants flourished, an entirely new group of animals emerged, many of them designed to thrive on the abundant vegetation. Picture yourself stepping back in time to the Miocene grasslands of North America, where you might see herds of Meropus, a creature that looked like a strange combination of a giraffe and a horse. Unlike its relatives, Meropus didn't walk on its knuckles. Instead, it moved with its feet flat on the ground, and its front limbs had large claws that made it bigger and stronger than others in its family. These creatures roamed the wide-open grasslands, which were also home to other fascinating animals like Synthetosaurs. This hoofed animal resembled an antelope, but had a huge two-pronged horn on the tip of its nose. At the same time, Aepycamelus, a tall relative of modern camels, wandered the land, towering as high as a giraffe. Along the coastlines, carnivores were evolving into new shapes and sizes. One example is Pinarctidian, an early species of walrus, which was bigger than today's walruses, but lacked the famous tusks. This massive creature would haul itself onto the rocky shores of the Pacific Ocean around 10 million years ago, resting and bellowing loudly between hunting trips. After the Miocene came the Pliocene, which lasted from about 5.3 to 2.5 million years ago. Though relatively short, it was a critical time in Earth's history, especially when it came to marine mammals. Fossils from this period show the presence of large sea creatures like Semirostrum, a type of dolphin with a large, extended lower jaw. This unusual feature may have helped it sift through the ocean floor in search of food. On land, the Pliocene brought major changes, especially with the rise of animals we know today, such as elephants. The American Gomphotherium, an early relative of the modern elephant, was similar to today's elephants, but had some important differences. It stood about 3 meters tall, had a long, jutting lower jaw, and special teeth designed for digging up roots. Its tusks curved downward, and it had an early version of a trunk, making it very efficient at handling food. Our next stop takes us to the Pleistocene, a time most closely linked to the Ice Age and the famous woolly mammoths. But perhaps more interesting than the mammoths were the mastodons, forest-dwelling relatives that were smaller, with flat, sloping heads and unique features. Unlike the mammoths, which were widespread across the northern hemisphere, mastodons were mostly found in North America. The Pleistocene also saw the appearance of Smilodon, the saber-toothed cat, a dangerous predator that would have been a frightening threat to early humans. Meanwhile, Arctodus, the short-faced bear, roamed the land, one of the largest bears to ever exist. The Pleistocene was also a time when dinosaurs made a brief return to North America in the form of Titanis, a giant, flightless, predatory bird. Standing tall like a terror bird, Titanis would have stalked the grasslands, hunting both small and large mammals. And then there's the amazing Megalonyx, Jefferson's ground sloth. These huge creatures, which lived during the Pleistocene, were much larger than their modern relatives, with incredibly long claws. These sloths used their claws to pull down branches, but also to protect themselves from predators. They were truly one of the most impressive creatures of their time. At the end of the Pleistocene, around 2.7 million years ago, the land masses of North and South America were finally connected by the Isthmus of Panama. This new land bridge allowed animals from the two continents to mix, leading to a major exchange of species. It also changed ocean currents and marked the start of a cooling period, with ice beginning to form in the northern hemisphere. During the early Pleistocene, which lasted from about 258 million to 0.8 million years ago, early humans from the genus Homo first appeared in Africa. These early humans slowly spread across the continent and into parts of Asia and Europe. At the end of the early Pleistocene, a change called the mid-Pleistocene transition occurred. This shift caused glacial cycles to last 100,000 years instead of the previous 41,000-year pattern, making the climate more unstable and extreme. In the late Pleistocene, modern humans left Africa and spread to other parts of the world. This period also saw the extinction of all other human species, with Homo sapiens being the only surviving human group. Humans were now in Australia and the Americas for the first time, coinciding with the extinction of many large animals in these regions. The Pleistocene continued the trends of cooling and drying that began in the Neogene period. The climate changed a lot, linked to the glacial cycles. At the peak of the Ice Age, sea levels were up to 120 meters lower than today. This drop in sea level connected Asia to North America through Beringia, and much of northern North America was covered by the vast Laurentide ice sheet. Although the land and ocean ecosystems were similar to those today, the Pleistocene was dominated by large mammals, many of which no longer exist. Mammoths, mastodons, giant sloths, saber-toothed cats, lions, tigers, and other huge creatures roamed the land. Some isolated places, like Australia, Madagascar, New Zealand, and certain Pacific islands, saw the evolution of giant birds and reptiles. These included the massive elephant bird, the moa, Haast's eagle, Quincana, Megalania, and Myolania. The dramatic changes in climate during the Ice Age had a huge impact on both plants and animals. As glaciers advanced, large parts of the continents were abandoned by wildlife, and many animals had to move southward, facing huge challenges due to the changing climate. The most significant threats came from the extreme temperature shifts, the shrinking of habitats, and the reduced availability of food. This period saw a major extinction event, wiping out many large species, including mammoths, saber-toothed cats, giant sloths, glyptodon, woolly rhinoceroses, and several species of large deer and bears. Even Neanderthals, who were another human species, went extinct during this time. As the Ice Age came to an end, cold-blooded creatures, smaller mammals like wood mice, migratory birds, and faster animals like white-tailed deer moved into the now warmed areas. Animals such as bighorn sheep adapted to the new conditions, becoming slimmer with longer legs than their ancient ancestors. Scientists believe the extinction of larger predators during the late Pleistocene caused animals to evolve differently, with species becoming more powerful rather than faster. Africa remained largely unaffected by these mass extinctions, but North America suffered greatly. Native species like horses and camels were wiped out, changing the continent's ecosystems forever.